Greetings. So welcome to today's session. Let me start off with the analysis of the quarter car model. So what are we going to learn with this quarter car model? We are essentially mainly going to analyze the ride comfort. Its quarter car model is typically used for analyzing the ride of the vehicle. We are essentially going to look at what is this quarter car model and how it can be used for ride analysis. What are the corresponding equations of motion and what are some consequent characteristics and properties of this model. Okay, so that's what we are going to look at. So as the name suggests, the quarter car model essentially considers one quarter of a car, right? So it can, as we know, a car is typically a four-wheel vehicle, and it is going to have four-wheel assemblies and four suspension assemblies, right? So the quarter car model considers one particular suspension assembly, and that's why it's called as a quarter car model. And what we typically do is that we visualize the vehicle to be split by the suspension as two units. What is called as a sprung mass, which is denoted by the character M subscript S. So this contains all the mass that is supported by the suspension, and what is called as an unsprung mass, which is denoted by the symbol M subscript U. This is present between the suspension and the ground, right? So for example, the wheel assemblies, any axles and so on, right? So the brake system, all those constitute what is called as the unsprung mass. Okay, and in between the sprung and unsprung mass lies the suspension elements. We have the energy storing element, which is denoted by a spring, and the energy dissipating element denoted by a shock absorber. So the energy storing element has a stiffness of Ks, and this is what is called as a suspension stiffness. And the energy dissipating element is represented by a damper or a shock absorber. And this is characterized by this, this is characterized by the parameter B subscript S, which is the suspension damping, which is the suspension damping. Okay, so these are the two main elements of any suspension. And the vertical stiffness of the tire is characterized by this parameter K subscript T, and that is the tire stiffness, okay, like as far as our ride analysis is concerned. So now, without loss of generality, we will consider an active suspension, and consequently, there is an actuator between the sprung mass and unsprung mass, and FA is the actuation force applied by the actuator. Okay, so this is without loss of generality. Okay, so we are just in general considering an active suspension. If you have a passive suspension or a semi-active suspension, like where this actuator is not there, this FA term will become zero. Okay, so that is what we are essentially dealing with. Now, this model is a 2 degree of freedom model. The 2 degrees of freedom being the vertical displacement of the sprung mass, which is denoted by the symbol ZS, okay, and the vertical displacement of the unsprung mass, which is denoted by the symbol ZU. Okay, so ZS and ZU respectively denote the vertical displacement of the sprung mass and the unsprung mass from their initial equilibrium states. And the input to the model is the road input, the road input, which is essentially denoted by ZR. Okay, so ZR is the input that comes from the road profile. Okay, so those are the main elements of this particular quarter car model. So as we discussed, so this is a 2 degree of freedom model. So what are the 2 degrees of freedom? The 2 degrees of freedom, the first degree of freedom is the vertical displacement of the sprung mass, which is denoted by the symbol ZS. Sprung mass, and the vertical stiffness is, the vertical displacement is denoted by the symbol ZS. And of course, that's a function of time. Okay. And the second degree of freedom is the vertical displacement of the unsprung mass. Okay, so the vertical displacement of unsprung mass is denoted by ZU. Okay, so ZU indicates the vertical displacement of unsprung mass. Okay, so these are the 2 degrees of freedom of the model. All right. So what we are going to do is that, like, we are going to draw the free body diagram of each of these masses, and then, like, we will write down the corresponding equation of motion. Okay, so that's what we are going to do now. So let's go through the process. So first, let's consider the sprung mass. Okay, which is given by denoted by ms. Okay, so if we were to draw the free body diagram of the sprung mass, please note that the sprung mass vertical displacement is going to be ZST. And what are the forces that act on the sprung mass? See, when we consider this quarter car model, what we consider is that, like, the car is initially assembled. So the suspension elements will have an initial deformation due to gravity, due to the weight of the masses, right? So we are going to consider ZS and ZU from that initial equilibrium state. Okay. So the springs and the shock absorbers are not at the free lengths, but rather there is an initial deformation which happens due to MSG and MUG. Okay. So we are going to start measuring or calculating ZS and ZU from that initial equilibrium state. Okay. So we need to keep that in mind. Why is that important? It becomes important because we are now consequently not going to denote MSG and MUG in the free body diagram. Okay. So that is where the consequence comes. Okay. So we won't see the weight being illustrated in the free body diagram. So what are the forces that act on the sprung mass? You know, like, we are going to have 3 forces. One force will be the restoring force from the spring. Another force will be the force due to the damping element. And another force will be due to the actuator. Okay, so let's mark all the 3 forces. So if we go back to this and we want to draw the 3 forces, so one force will be the restoring force due to the suspension spring. Or say, what will be the restoring force due to the suspension spring? It will be Ks times Zs minus Zu. I'm suppressing time, parenthesis time with the symbols, because for brevity. So that will be the restoring force from the spring, assuming a linear spring, assuming a linear shock absorber. The force applied on the mass due to the motion is going to be Bs times Zs dot minus Zu dot, Bs being the damping coefficient of that damper, of the suspension damping element. And let us assume that without loss of generality, the force that comes from the actuator, okay? So, sorry, let us assume that the force that comes from the actuator and acting on the sprung mass, let it act upwards, okay? And let's call it as some F8, okay? So that is the force coming from the actuator, okay? So consequently, the equation of motion of the sprung mass is going to be the following. So what is the equation of motion of the sprung mass? Okay, so equation of motion of the sprung mass is going to be equal to, sorry, ms times zs double dot t. That's going to be equal to the net force. M times A equals the net force acting on this mass, right? So the net force acting on the mass is going to be equal to Ks times ZST minus ZUT minus Bs times Zs dot T minus Zu dot T. Zu dot T plus F8. Okay, so without loss of generality, we are assuming F8 to be acting upwards. Okay, it can be acting other directions, no problem. So if we combine this equation, what we are going to get is the following. We are going to get ms times zs double dot t plus bs times zs dot t plus ks times zst okay, minus ds times zu dot t minus ks times zut, that's going to be equal to F8. So by the way, how is the displacement of the spring equal to Zs minus Zu? Please note that if the sprung mass moves up by Zs and the unsprung mass moves up by Zu, as indicated in these diagram, the extension of the spring will be the difference between the two, right? The difference between the two displacements is Zs minus Zu. Okay, so that is why the restoring force from the spring is written as Ks times Zs minus Z. Okay, so I hope that point is clear to all of us. Okay, so this is the first equation. Okay, so this is the equation of motion for the sprung mass. Sorry, of motion for the sprung mass. And now we can write a similar equation for the unsprung mass. Okay, so let us call this equation as equation number 1. Okay, so we are going to process this equation as we come later. Now, let us go and draw the free body diagram for the unsprung mass. Okay, so let me indicate the unsprung mass now. So the unsprung mass is indicated by mu, and the corresponding vertical displacement is ZUT. Now, what will happen to the corresponding forces by Newton's third law of motion? Now, what will happen is that Ks times Zs minus Zu will act upwards. Ds times Zs dot minus Zu dot will also act upwards on mu. Okay, and Fa will be acting downwards. Okay, so that's what will happen with the free body diagram of the unsprung mass. Sorry. Yeah. So I hope it is clear how we have drawn this diagram. Okay, so I'm just going to mark FAT alone here, but I hope the other two, it's clear how we got the other two forces, right? So the same three forces, the directions are going to be flipped, okay, when we draw the unsprung mass. But in addition to these forces, we will also have a restoring force from the spring, which is characteristic of the tire stiffness, and that's going to be equal to Kt times Zs minus Zu. Okay, so that is the other force we are going to get. Now, we can consequently write down the equation of motion of the unsprung mass. So the equation of motion of the unsprung mass is going to be the following. So what will be the corresponding equation of motion? Let me write it down. So the equation of motion of the unsprung mass, once again, we have to write ma equals F. So now ma is going to be mu times Zu double dot T, and that's going to be equal to the net force acting on it, right? So let's write down each term. So considering the upward direction to be positive, so we have Ks times Zs minus Zu as the first force, then ds times Zs dot minus Zu dot, that is the second term. Then we have a force from the tire stiffness, which is Kt times Zs minus Zu. Oh, sorry, not Zs minus Zu. Okay, I made a mistake here. Sorry about that. So 1 minute, let me retract. So this displacement will be Zu minus Zr. Sorry about that. Okay, for the tire stiffness, the displacement, the vertical displacement of the corresponding spring, the extension is going to be Zu minus Zr. Okay, so consequently, the equation also will change. Okay, sorry about that. Please correct that diagram. So this is going to be equal to Kt times Zut minus Zrt. Okay, so that's what we have in this particular equation. Okay, as coming from the tire. Okay, of course, then we have minus F8. Okay, so this is one other term which comes in. All right. So now we are just going to rewrite this equation as the following. So this will give us mu times Zu double dot T plus ds times Z U dot T plus Ks plus Kt times ZUT. That's going to be equal to, sorry about that. Let me not write equal to. You will understand why I'm writing it this way. I'm just collecting terms in a specific manner. Minus Ks times ZST minus Bs times Zs dot T. That's going to be equal to minus FAT plus Kt times ZRT. Okay, so this is the second equation. Okay, so let's call this as equation number 2. All right, so this is the second equation of motion. Okay. So let's call this as equation number 2. Now, what we are going to do is the following. Okay, so we are going to collate equations 1 and 2 and then represent them as a vector OD. Okay, so that's what we are going to do, right? So please note that both equations 1 and 2 are two separate second order linear ordinary differential equations. Okay, so what we are going to do now is that we are going to combine them as a vector second order linear ODE. Okay, so how do we do that? So let's see how we can do that. Equations 1 and 2 can be rewritten as or expressed as the following. Okay, so what do? We are going to collate terms. So the first term, we will collate the inertia terms. So the inertia terms will involve the acceleration. So essentially, we'll have Zs double dot and Zu double dot T terms. Okay, so I will fill up the matrices shortly. Okay, so I'm just first explaining the physics, and then we will write the we'll fill up the blanks. Okay, the second term is going to involve the damping term. So that will involve the first derivative of Zs and Zu. So we'll have Zs dot and Zu dot. Okay, then the third term will involve the stiffness terms. So this will have Zs and Zu. Okay, and we are going to write on the right hand side. Let me give some space here. Okay, on the right hand side, we are essentially going to write two terms. So the first one is the exogenous input which comes on the system, which is ZR. And the second one, if you have an active suspension, it's a sort of like a control input. Okay, so which is something which we can regulate. Okay, so this is how we are going to write this equation. So if you look at the first equation, these two equations, right, 1 and 2. So we can see that it has all these inertia terms, the damping terms, and the stiffness terms, and so on, right? So we are going to collate them. That's all we are going to do. Okay, so let me fill up these matrices. Okay, in this consolidated equation. So we can immediately see that we are going to get ms00 mu. Okay, as the first term, multiplying the acceleration terms. Then we have Bs minus Bs. This is also minus Bs. This is plus Bs. Okay, multiplying the velocity terms. Then we have Ks minus Ks minus Ks. Okay, and then Ks plus Kt, multiplying the displacement terms. And then multiplying the road input, we have 0 and Kt. And then multiplying the actuation force, we have 1 and minus 1. Okay, so these are the terms that we have. So this vector, which involves the two displacements that are the 2 degree of freedom, let's call it as the vector Z. Okay, I'm just putting a tilde underneath Z to indicate that it's a vector. So consequently, this will be a Z dot. Okay, that will be the velocity term. And this vector will be the acceleration term. Okay, and this 2 by 2 matrix, okay, is indicated by M, and this is the mass matrix. It's a diagonal matrix which multiplies the acceleration. That's why it's called as a mass matrix. This 2 by 2 matrix, BS minus BS minus BS and BS, is what is called as the damping matrix C. Okay, so because that indicates the dissipation that is happening, right? The damping which is happening in the system. So that is why it is called as the damping matrix. Okay, this matrix is denoted by capital K. Okay, and this is what is called as a stiffness matrix, right? Because these terms, when multiplied by the displacements, give us the restoring force due to the springs that are appearing in the system, right? So that's why we are calling it as the stiffness matrix. Okay, let's call this vector as some vector B1, which is multiplying the road input. This vector as some vector B2, which is multiplying FA. And then we can sort of collate and rewrite this entire equation into this consolidated vector ODE. Okay, this is the second order vector ODE. We are essentially rewriting this form. Okay, M times ZS double dot plus C times Z dot plus K times Z, and that's going to be equal to B1 times ZRP plus B2 times FAT. Okay, so this is what we will have. Okay, so this is a generic form of such multi-degree of freedom systems. Of course, on the right hand side we have specific inputs here, but then like this is how the quarter chord model can be represented as a second order linear vector ODE. Okay, so now we are next going to ask ourselves the question, what are the corresponding natural frequencies of the system? Okay, so before we go there, any questions on what we have done till now?
So the metric equation we have mentioned here, is it state space representation?
It is not state space. Okay, so why is it not state space? The reason why it is not state space is because it is essentially a vector ODE, and we can see that the highest order derivative term which is coming in that equation is second order, right? In the state space representation, we rewrite an nth order ODE as n first order differential equations, right? Good question. Okay, so I'm going to leave that to you as an exercise for you to do. Rewrite the same equations in the state space representation as an optional exercise. Okay, now that you have asked that question, okay, this is a good time for me to give it to you as an exercise. Okay, so I was about to give it at the end of the class. Okay, so this is a good point. Okay, so this is not the state space representation, rather it's a vectorized form of the two ODEs. Okay, so as an exercise, please write down the state space representation. Okay, you need to now, what you need to do the state space representation for both equations on 1 and 2, choose two state variables each. For example, for equation 1, you can choose ZS and ZS dot as two state variables. Similarly, for equation 2, you choose ZU and ZU dot as two more state variables. See whether you can write it in the state space. Okay. Yeah. All right. I hope that answers your question. No, sir.
Yeah, yes, sir.
Okay. So this is an optional exercise just for our learning. Okay. This is a good question. So I will preemptively give you this exercise. Write down equations 1 and 2 in the state space representation. Okay, you don't need to submit this as a homework, just for our own learning. All right. Okay, any other questions?
In this quarter car model, sir, can you just quickly run through how the forces are like getting applied and we are getting
So just let's say, for example, for visualization, right? Let us say this mass ms is getting pulled up in this direction. Okay, just for the sake of argument. Okay, without loss of it can go down or go up, right? It doesn't matter, right? Is it not? Okay. Let us say at the same time this unsprung mass is also going up, right? What is happening? You consider the spring. This end is pulled up by ZS, right? This end is pulled up by ZR. So what is the effective stretch of the spring?
So ZS minus ZR.
ZS minus ZR is going to be the effective stretch of the spring, right? Is it not? And so consequently, the restoring force from the spring will be Ks times ZS minus ZR, right? Is it not? Okay. Yes. So that's what we have written here. Oh, ZS minus ZU. Sorry, I'm sorry. This is not ZR. Sorry about that. Yeah. Sorry. Sorry about that. Let me see how I can make this ZU. Okay, so this is going, oops, sensitive. Okay, this is going to be ZU. Sorry about that. Okay, so the bottom is going to be pulled up by ZU. So, but you get the idea, right? So the spring is going to be stretched by ZS minus ZU, right? So that is why the restoring force is Ks times ZS minus ZU. And the direction is downwards. Why? Because without loss of generality, we are assuming the mass to move upwards, right? Yeah. Same argument for other masses also. Okay. Yeah.
Yes, sir. So this FAT is inertial term. No.
What's it?
F is what input, sir?
Which one? No.
Sir, FAT.
FAT comes from the inertia. Okay.
Okay.
Yeah. So essentially, what happens is that like FAT is sorry, not from the inertia, from the actuator. Sorry. So you see an actuator here, right? So yeah. Okay. So if you have an active suspension, you put an actuator between the sprung mass and the unsprung mass, and that results in the actuation force. Okay. Okay. If you see in typical car suspensions, this FA will be 0. Okay. So FA for passive suspensions, passive and even semi-active suspension, okay, where we don't have this actuator, for passive suspensions, this FA will be identically equal to 0. Okay, because there is no actuation, explicit actuation force that you and I can control. Okay.
Sir, FA, okay, sir. Active, this it will only adjust the damping, right, sir?
Okay. We will learn more about it when we go to automotive controls. In a fully active suspension, you can design this FA, okay, to adjust what is the level of force that you want to put on the sprung mass and unsprung mass to get some desired suspension performance. Okay. So it is not damping alone, right? So it is an actuator. It can be a hydraulic actuator, it can be an electric actuator, electromechanical actuator, which applies a variable force, right? Yeah.
Yes. Okay.
Okay. So see, for example, let us say, let's say, let's picturize this, right? Let's say we are driving a car, right? And I am going to go into a pothole, right? So what is going to happen to me? Suddenly, my tires are going to go into a pothole, and I'm going to feel some impulse forces on my seat, right? But imagine, like putting an actuator which will compensate it for it, ahead of time, so that I don't feel the force at all, right, on me, right? So that is an active suspension, right? So that's how FA comes in. Okay, that's where FA comes in. Okay. Yeah. All right. Okay. Any other questions before we move on?
So road input here, it means the unevenness of the road, or it's a tire compression?
Unevenness of the road, right? So you will have different road profiles. Okay. So there are ISO standards which grade the road profiles based on the roughness. Right now there is class E to class H, right? Okay. So you will have different road roughness profiles. Okay. And ZR is the, see, if you have a smooth, flat road, ZR is 0, right? But that's not how it is in real life, is it not? Okay. Yeah. ZR is the displacement experienced at the tire road interface due to the road even unevenness or road roughness. Okay,
Okay, sir.
any other questions? Okay, so if not, let's go ahead. So now the next task that we are going to do is that, like, see, it is a standard process in most vibration problems, right? We determine what are the modes or the natural frequencies of the system. Okay, so that is what we consider. So consequently, yeah, this exercise, as I said, it's an optional exercise for you to do. So let us now consider, but please do this optional exercise, because when we come to automotive controls and when we do suspension control, we would require the state space representation of the quarter car model. Okay, so it is better that we do it in this course and then like we apply it in the next course on control of automotive systems. So let us now consider the undamped and unforced system. Okay, so that is what we are going to consider. Why are we considering the undamped and unforced system? Because that is the definition of natural frequency, right? So what is the definition of natural frequency? It is the frequency at which the mass will oscillate when the undamped unforced system is subject to some perturbation, right? So if the system is undamped, Cx dot becomes 0. If it's unforced, the right hand side becomes 0, right? Zr is 0, Fa is 0, and so on, right? So we are only left with mx, m times z double dot plus kx, k times z of t equal to 0. So this is like mx double dot plus kx equals 0 that we saw in the previous class, right? For single degree of freedom systems, you remember? So when we discussed the natural frequency for the single degree of freedom mass spring damper system, when we consider the undamped unforced system, we ended up with mx double dot plus kx equals 0, right? And we figured out that the natural frequency is square root of k by m. So similarly, what we are having is that like we are essentially going to look at the undamped and unforced system, and then like we are going to have this particular equation, right? So that's what we are going to get. So it so turns out that this is a result. Okay, I'm not going to prove this. So how do we get the natural frequencies of multi-degree of freedom system? So the natural frequencies of multi-degree of freedom systems, because which are expressed in this form, multi-degree of freedom systems, can be obtained by solving determinant of minus omega squared m plus k is equal to 0. Okay, so that's what we. So this is an important formula. This holds true for any multi-degree of freedom system. Okay, all systems whose degree of freedom is greater than 1. Okay, so this formula holds true. All right, that's how we calculate the multi-degree of freedom system. So now, if I were to apply it for our quarter car model, for the quarter car model that we are considering, what do we have? So for the quarter car model, the mass matrix M is going to be equal to ms 0, 0, mu, right? So we know this, and the stiffness matrix K is going to be equal to Ks minus Ks minus Ks and Ks plus Kt. Okay, so that's how it will come out as. So now consequently, if we want to solve determinant of minus omega squared m plus k equal to 0, what do I get? Okay, so I am going to write down the important steps. Intermediate algebra steps I'm going to leave it to you as an exercise for you to do. I'm sure you can figure that one out. So first let's write down determinant minus omega squared m plus k. Okay, so how do I get minus omega squared m plus k? First I multiply the mass matrix by minus omega squared and then add the stiffness matrix K2. So it will become minus omega squared ms plus Ks. And then like we'll have minus Ks then minus ks, and then like we have minus omega squared mu plus ks plus kt, okay, and that's going to be equal to 0. All right, okay, so this is what we have, and this is going to give us ms mu omega power 4, okay. We are just cross multiplying the terms, right? And then like we'll have a coefficient for omega squared, ms times ks plus kt plus mu times ks omega squared plus ks. I'm just cross multiplying, okay? I'm not doing anything more. Ks times ks plus kt minus ks squared is equal to 0. Okay, so this is what we have. So in fact, if we simplify this constant term, this will come out as ksk. All right. Now, one may wonder, hey, how are we going to solve this equation, right? Because it looks like this is an equation in omega power 4, right? It's the fourth order of omega, right? But then we need to get expressions for omega, right? How do we solve these equations? So please note that in this particular equation, we are only having even powers of omega. Okay, so that is something which we are going to use to our advantage. Please note that there's only omega power 4 and omega squared and the constant term. Okay, so what we are going to do is then let omega hat, okay, we define another symbol omega hat be equal to omega squared. Okay, so I hope all of us get the idea as to what's going to happen. So if I do this, I am going to have ms mu omega hat squared, okay, minus ms times ks plus kt plus mu ks omega hat plus ks kt is equal to 0. Okay, so that's what we have. Then I can immediately solve this. How? Because please note that this is a quadratic equation, right? So we are aware of quadratic equations of this form: a s squared plus bs plus c equal to 0. If we have such an equation, the solution to this quadratic equation is going to be minus b plus or minus square root of b squared minus 4ac divided by 2a. Okay, so that's going to be the solution for such quadratic equations, right? So we are going to use the same formula here. Only thing is that like it's a quadratic equation in omega square. Okay, so consequently, the solution to this equation will be omega n square, right? So I'm just inserting the parameter, symbol n here, just to show that this is the solution that we have to this equation, and the solutions are going to be the natural frequencies. So minus b is going to be ms times ks plus kt plus mu times ks. This is going to be a rather long expression, so please bear with me. Then we are going to have plus or minus square root of b squared minus 4ac. So what is this b squared? We are going to have ms times ks plus kt plus mu ks the whole square minus 4 ms mu ks kt. That's minus 4ac, right? So that's what we are doing. Okay, why am I doing this? Because please note, if I were to do this, this coefficient is now my a, minus this coefficient in the square bracket is b, and kskt is my c. Okay, so we are just using that formula. All right, so that's all we are doing. Divided by 2 times a is ms mu, right? So we get 2 times ms times mu. Okay, so this is going to be our equation for omega n square. Now I leave it as an exercise for you to do. Once again, an optional exercise, but please do this. So omega n square, the solution we will get as if you simplify this equation, you'll get it as Ks plus Kt divided by 2 times mu plus Ks divided by 2 times ms plus or minus square root of, it's going to be a rather long expression once again. So let me write it down. Ms square times Ks plus Kt the whole square plus mu square Ks square minus 2ms mu Ks Kt minus Ks. Yeah, please bear with me. It's a rather long expression, but then like we will see some interesting physical insight from it short. Okay, so that is why I'm leaving the algebra, intermediate algebra to you as an exercise. Okay, but please do it. So that's going to be divided by 2 MSN. Okay, so this is going to be our final expression. Okay, so this is going to be a final expression. So going from here to here is an exercise, which I leave to you. All right. Okay, so I leave this to you as an exercise so that you can essentially do it at your own leisure. Okay, so please do it as an optional exercise, but then like please try it out. Okay, so simplify it. All right. So, but then at first glance, this looks like a rather long expression, right? So let me quickly recap what we have done. We have written down the equation of motion, and then like we have essentially used the formula that we use for getting the natural frequency of multi-degree of freedom system, which is determinant of minus omega squared m plus k equals 0. And when you solve that equation, we get this rather long expression, right? So then what do we do with this? So now we are going to do a simplification. Any questions on this derivation till now? We are going to do the last part of the derivation now, and then we'll see something interesting. Okay. So when the tire stiffness Kt is much higher than the suspension stiffness Ks, what happens? The tire stiffness Kt happens to be much higher than the suspension stiffness Ks, then the following simplification happens. So what happens is that Ks plus Kt becomes almost equal to Kt, and Kt minus Ks also becomes almost equal to Kt. Okay, so that's the simplification we get. Okay, how is that? You know, like the bottom line is that, like, if you look at, you know, the suspension stiffness and the tire stiffness, let's say they are separated by an order of magnitude, right? Let's say, you know, just to convey the concept, right? Let's say Kt is 10, right? And Ks is some 1. Okay, so there is a 10:1 ratio. I can always say 10 plus 1. Of course, I know that it's 11, but then I can say it's almost equal to 10. Similarly, 10 minus 1, which is 9, I can say it's almost equal to 10. All right, so that is the approximation we are doing. So then what is our impact? We will see an impact here. Okay, here Ks plus Kt will become almost equal to Kt. Here also Ks plus Kt will almost be equal to Kt. And here also Kt minus Ks will almost become equal to Kt. Okay, so these are 3 places where we will get an approximation. All right. So with this approximation, what will happen to this expression? The expression for omega n square will become Kt divided by 2 times mu plus Ks divided by 2 times ms plus or minus square root of ms square kt square plus mu square ks square minus 2ms mu ks kt divided by 2ms mu. Okay, so this is what we have. Now, once again, I'm going to leave you with an exercise. If you do this, you can simplify this as, finally, you will get two solutions. Of course, this is an approximation, right? I should be very careful. Sorry about that. So this is approximately equal to this, right? Please simplify this. And ultimately, you will get two nice, very simplified expressions, okay, after all these derivations. So we will get these two expressions. Okay, so once again, I'm going to leave this as an exercise for you. Okay, how did we go from here to here? Just maybe a couple of intermediate steps. Okay, but a simple algebra. Please do try it out. Okay, so with this, what's going to happen is that, like, we are going to get two expressions for the natural frequency corresponding to the quarter car model. And they are going to be approximately equal to square root of ks by ms and square root of kt by mu. Okay, so this is an interesting result, right? Why? Because what we are saying is that we know that the quarter car model is a multi-degree of freedom system. Okay, it is not a single degree of freedom system, right? Only for a single degree of freedom system, we saw that the natural frequency was square root of k by m. Right? For a multi-degree of freedom system, it's a very complex equation, right? As we just derived. However, when the tire stiffness is much higher than the suspension stiffness, which is typically reasonable in practice, we get a very much simplified expression for the two natural frequencies. So in a way, the quarter car model decouples into two first order models. Okay, so wherein we have the square root of ks by ms corresponding to what is called as the natural frequency corresponding to the sprung mass mode. Okay, that's what is called. These are two modes of vibration. Okay, this is what is called as a sprung mass mode. Okay, and the second frequency, square root of kt by mu, corresponds to the natural frequency, sorry. Yeah, 1 minute. So the second mode corresponds to the natural frequency corresponding to the so-called unsprung mass mode. Okay, so this is what is called the unsprung mass mode. All right. So we see a nice decoupling, right, in the 2 degrees of freedom. Okay? So when the tire stiffness is more than the suspension stiffness. So this quarter car model, yes, any questions?
If both the natural frequencies are same, like equal, then there will be a resonance and there will be a problem, right?
1 minute. Let me answer that question one by one. Like, let me make a couple of statements. Okay, so let me repeat your question. What happens if this omega n1 and omega n2 become the same? Okay. So first is, can they become the same? Okay. Let's analyze it. So please note that kt is much higher than ks and mu is much lower than ms. So consequently, the ratio of kt by mu is going to be much higher than ks by ms, right? Is it not? So even these natural frequencies are typically separated by an order of magnitude. So if this omega n1, which is square root of ks by ms, is of the order of 1 hertz, okay, omega n2, which is the second natural frequency, kt by mu, will be of the order of 10 hertz. Okay, that's point number 1. All right. Okay, so the point is, it's very unlikely that they are going to become the same. So, but then now what happens if they happen to be the same? Will we get resonance? See, resonance, please know, is essentially, as we studied previously, happens with stable second order system. When the input to the system, right, it's a damped system, right? When the frequency of the sinusoidal input that we are providing matches the resonance frequency. All right. So if, let's say, due to some reason, okay, very unlikely, but let's say due to some reason, if omega n1 equals omega n2, what happens is that, like, when we don't have a undamped, unforced system, if we perturb both the masses, both of them are going to oscillate at the same frequency. Okay, so that is their physical interpretation. All right. So I hope that answers your question. Okay?
So, thank you.
Okay. Yeah. So, but I hope it's clear why they are very unlikely to be equal in the first place. All right. So, yeah. And if they're equal also, they will essentially have the same natural frequency. That's it. Okay. Yeah. So this is a very nice decoupling that we get when the tire stiffness is much higher than the suspension stiffness. Okay. So this is the quarter car model. So we'll be using this later on in the automotive controls course to do more analysis of ride and then like do even like active control design. So that is something which we will do subsequently in the control of automotive systems. All right. So this is what I wanted to share with you today. We will continue in the next class and then we'll look at half car models. Are there any questions about the quarter car model? All right. So if not, let me stop recording. Thank you.